Swayam Prabha. Digital India. Educated India.
All right. So this D is basically the forcing vector. So this is your data vector or vector of the quantities you want. So this can be called as some sort of a stiffness matrix. If you have learned finite element, I wouldn't like to use the word stiffness matrix because the Z is basically called as the Jacobian matrix. Jacobian or sensitivity. So in this case, this was a simple problem in which temperature was a function of time. If temperature is a function of time x, temperature is a function of x, y, z as well as time, or temperature is a function only of x, y, z. Since this contains partial d with respect to partial t for this case, the partial t with respect to a and b in this case, if it's a large matrix, you can actually take a very close look at the Jacobian and see which of the values are very high, which of the values are very low. This tells you the sensitivity of the temperature to a particular parameter. Okay, so this could be because the heating is taking place at one place in the problem and you're measuring the temperature at some other place and so on. So you could be actually putting both thermocouples in the wrong place. For example, let's say a fin problem. You're using a fin. Let's say you're using a fin in the heat transfer lab to solve it as an inverse problem to get an estimate of the convective heat transfer coefficient. Let's say that you are measuring some temperatures here, T1, T2, and Tn. Okay, and then you are just proposing that sigma theta I minus theta fit I whole square equal to I into 1 to n. Let's say you want to minimize this. And this theta fit I is a function of cos HML, sin HML. From that you're getting m equal to root of hp by k. If k is known, a is known, h can be found out. If h is known, k can be found out. So many other permutations and combinations are possible, because sometimes when something is working, you don't know the actual h. You might have designed it with some h based on the continuous data which some equipment is giving after it is operational. So you want to do this. Now, if you have only 10 thermocouples, the funda is whether you want to put the 10 thermocouples here, 10 thermocouples here, 10 thermocouples here. See, if you're just a data scientist, this will not help. You have to be a heat transfer. You have to be a heat transfer specialist. The temperature goes like this. This you know. Temperature is a function of wave. Therefore, the maximum gradient of the temperature occurs near the base. And here it is almost approaching T infinity. Therefore, if you have 8 thermocouples, if you have placed all the 8 thermocouples, because it's easier to measure here, this means you are a very good data scientist, but you have absolutely no idea of heat transfer. This will give you a wrong error. It will give a wrong value of h, because if you take the Jacobian, the dou of t divided by dou of m or dou of t, dou of h, this will be very low value. Okay, it is giving very low values because the temperature anyway is not changing. So just like they say, you should know where you should put your money. Much in the same way, you should know where you should put your thermocouples. Where should you put your strain gauges? If you are in stress analysis, if you are in the business of stress analysis, if you are in the business of stress analysis, or where will you put your heat flux gauge in a re-entry missile or a PSLV? This thing you want to measure. Once it is flying, you want to measure. Where will you put your strain gauge? Where will you put your heat flux gauge? In all these cases, domain competence is very much essential. All right. So that is a Jacobian matrix. So we'll see more about the Jacobian matrix in a later class. Okay. But for starters, so this is fine. So what you have to do is you have to start with a particular value of. You will start with a particular value of AB. You will start with a particular value of AB, and then evaluate the Jacobian, evaluate the Z, evaluate the Z transpose Z. Then for that particular value of A and B, you will calculate the theta fit. Okay. Then this Y data minus Y fit, that will be a column vector. You'll get the D and solve this equation. Solve the system, get delta A. Get the new values of A, B, and A new and B new. Proceed till you obtain convergence. Okay. Now this is basically the method. There are some methods available, specialized techniques to improve the Gauss-Newton algorithm, which we'll see in a later class. But now the objective of today's class is to give you an idea of what is the motivation for studying this Gauss-Newton algorithm in a heat transfer problem, a case for nonlinear regression. Please mute yourself. Sai. Okay, I think whenever people log in, they are not able to mute automatically, right? It takes some time. So I know that somebody is logging in when that sound comes. Now consider a body like this. Okay. Consider a body like this. It is having a mass M, specific heat Cp. Okay. Volume V. This is a surface area. Okay. It is using heat by convection to the surroundings at T equal to 0. T equal to Tr everywhere. And T is a function only of time. Okay. And Ti is greater than T. Okay. Is the object cooling or heating? Is the object getting cooled or getting heated? Hello.
Cooled.
Object is getting cooled. So how many people are there in the class? Rajesh, you should activate the attendance.
Okay.
Suraj is not there or Suraj is there?
Yes, sir. Yes.
Yeah. So you're ready with the problem, right?
Yes, sir.
Yeah. You're watching what's going on, right?
Yes, sir.
Okay, fine. After I complete the example, you can show the problem. All right. Okay. Now, consider a situation like you may think, sir, we already solved this problem. Okay, hang on. We did solve this problem in the previous class. You're also doing it as an assignment, which is due for submission tonight. Assignment test is due tonight, right?
Yes,
Rajesh? Okay, so the submission link, you can just send a reminder again. You can send the link again. Somebody will ask, somebody will miss, and then they will post it on the group. Send it by WhatsApp, email, and Moodle today. Is it okay after the class?
Okay.
Okay. And also just please say that, send a mail that if there is a problem, people should send an email before 23:59. You should not discover a problem and say, this is the problem, that problem, I did not anticipate. I keep saying the same thing, right? So you can't do this. You can't do this if you have a US visa interview or something. I mean, you have this thing. If there is a problem, submit now. Already it takes only 1 hour to solve the problem. Forgo the lunch today, 12:30 to 1:30, sit tight, finish it, upload it, and then if there is an internet problem, discover it at 1 o'clock in the afternoon, go somewhere, figure it out, take somebody else's mobile, do whatever you want, but it has to be done. So can we find out reasons why PSLV today this is not good, we cannot launch, tomorrow we'll launch, after 2 hours we'll launch, I mean, so it basically gives you an idea of how much priority you have. If it is very important, do we miss flights? Because we can give many reasons. So that's why I keep saying. So if you're taking an exam 50 minutes, if you're taking 3 minutes, it's okay. If you already have a 5-day deadline for just 2 questions, it is not fair at all for you to say, sir, I want 10 minutes, I want half an hour, this is not working, let anything, let some things not work. It's fine. But find that out at 6 o'clock in the evening. Don't find at 11:59 and then say that it is not working. So if there is a problem with your email, if you're not, if with your Google link, you feel that it won't work, submit it by email, not to me, because there's a good chance I will miss it. So submit it as an email to Rajesh Akula with a copy to. Will you send that? No? Rajesh, will you send that mail to where they should send? Rajesh.
Sir.
Yeah. Please send a message to them so that they can submit it by email if in case of a problem to you with a copy to Suraj Kumar and not to me.
Okay, sir.
Is that okay?
Yeah.
So this mail has to reach before 23:59. All these reasons should not come after the deadline is over. Any reason, you can have any valid reason. Let the reason be now 2 o'clock, 3 o'clock, 4 o'clock, 6 o'clock, 8 o'clock, not at 23:59. Okay. Now you may be wondering, I will send an email to sir. What is the problem? I will show you. Okay. 1 second. Yeah. I will share the screen. Are you able to see my screen? Are you able to see my screen? Can somebody respond?
Yes, sir.
Please see the number of emails in my box. So you please don't bombard me. It's not that I want to help you, but it's quite possible that this because some announcement, somebody got an award, somebody published a book, all that. See the 31,000 emails I have not read. See how many things are coming from the morning. It's incredible. It's 9:35 a.m. See this. 4 o'clock, 12 o'clock, 11 o'clock, 12 o'clock. Then don't tell me at 23:59, sir. Then you don't even copy to Rajesh or this thing. It is my responsibility, right? So I have sent it to sir. He will take care. How will I take care? I'm having 33,000. See, International Journal of Thermal Sciences. I'm an editor. See, if you just put International Journal of Thermal Sciences every day, hundreds of mails will come on International Journal. You don't even know. You think that that this is the only thing we do. Of course, it's very important. I love teaching all. You think that I am just waiting for your email. There is no, so if there is a problem, that 8 emails alone I will get and then I have no other work. That is a problem. See, International Journal of Thermal Science, in between some Citibank, everything will come. Somebody has a royalty statement, somebody has a problem, somebody wants to do a postdoc. How many mails can we handle? Is it okay? So please have mercy. So if you want to know what a prof is doing, I open my, it's all transparent. You've seen my inbox. This 30,000, I want to reduce it to 25,000, but this I will do only during the break. This may be some mail on 23rd June 2018 or something, right? So I don't even know what it is. But if it is important, I would have seen. My funda is, if something is very important, somebody will say, sir, I invited you. You're supposed to read a PhD thesis. So I will get a reminder. If I don't get a reminder, it may be still in the inbox. Therefore, please appreciate that since it is specifically concerning this course, there are 2 TAs assigned to this course. If there is something, write to the TA with a copy to me if you feel that I should see it. If you have faith in the TA and anyway, if there is a problem, you will escalate it to me, then just submit, give it to the 2 TAs. Anyway, if there is a major decision they have to take, they will not take without consulting me. Is it okay? So just please understand. So you just see the amount of traffic, on my official email. So it is, then there is if I go into my inbox of the International Journal of Thermal Science, that will be another shocker. Every day, some 10 people are submitting, some 8 people are asking questions, what happened to my paper? Like that, every professor will have some other thing. There will be some other thing which we are doing. All right. So just be aware. Okay, I'll stop sharing. All right. Okay. Now the sharing has stopped. Correct?
Yes, sir.
All right. Okay. All right. So now the spin now is the spin. Already we have seen there is something which is cooling. Okay. already we have seen this. The spin now is the body is generating the body is generating heat uniformly at the rate of QV watts per meter cube. Okay, so therefore this Q is equal to QV to W watts per meter cube. Now, if you start solving this problem, so the governing, so goal. What is the goal? Can we get? So can we get T as a function of T? So the goal is, can we get T as a function of T? That is a question. That is a question we want to answer. Okay. So for that, you have to formulate. Is the problem clear to you? So it looks very much like the cooling of a aluminum slab, or I think this problem is there in the assignment test also, isn't it? Rajesh, is it the first question of the assignment test? Suraj? Suraj?
Sir?
Is it the first question of the assignment test that is without the heat generation?
No, sir. Not,
What is the first question?
first question like some simple questions, sir, regarding some class, how many class in IIT Madras, like this.
No. Assignment test 2 first question.
This is assignment.
Assignment test 2 first question, Suraj.
First
Just try to catch what I'm trying to say.
question.
Assignment test 2 first question. What is the question?
Sir, it is cooling of aluminum bar in still air.
That's what I'm saying. Suraj, you have to help me. You have to help me.
Sir, this is assignment.
Yes, sir. No, sir. Say.
Sir, assignment. This is assignment test 2, sir, not 1, sir.
Whatever it is.
Yes.
What I meant was, this problem we discussed. Assignment 2, assignment is all names we have given.
Yes.
What I wanted to tell the class was, I wanted them to connect it to what they are already solving this problem. That is my idea. Students, did you get what I was trying to say?
Yes, sir. Without heat generation.
Okay, fine. That's fine. Okay. Yeah. So it is there. So this variant you've already seen, except that the heat generation is not there. Okay. All right. Now the governing equation will become. So the governing equation is mCp dt equal to Q minus HA is to T minus T. Okay. Now, let theta be equal to T minus T. So, therefore, mCp d theta by d tau equal to Q. So, this is Q, this is theta. This is Q minus HA into theta. Now, we have to solve this. Okay. So, please note that this is different from the whatever you have solved in the assignment test 2 or whatever you considered in the class so far. For a simple cooling problem, it is only like this. Now, it is Q minus. Therefore, there is something which tries to heat it up. There is something which tries to cool. Therefore, so what will happen is the body is continuously trying to cool, but there is an internal heat generation. So when time t tends to infinity, so this dt by d tau will tend to 0 because the body will attain some steady state. Before that, if it is so high, if the Q is so high, it may even melt and collapse, whatever. But generally, it is possible that there is steady state. It's highly likely that a steady state will be approached. If that is the case, then Q will be equal to HA into theta S, where theta is the steady state temperature excess. Theta S will be Ts minus T infinity. Ts is the steady state temperature. Okay, so if you plot it, so the situation will be like this. Now I'm not even going to the solution. I'm just looking at the fundas. The plot will be like this. EI, TS, T. This is the cooling. This is the heating of a first order system with a constant heat generation and a constant heat transfer coefficient. Okay, so this is the this is what we are trying to model. The forward problem is, given all these values, can you tell how the system responds or how? So, for example, can you tell me what is the temperature here? This is the goal of modeling. This is the goal of modeling. This is the goal of all analytical enterprise. So we have studied all this from primary school, middle school, high school, JE, BTech, MTech, PhD, whatever. The goal is analysis. We want to find out. But now the inverse problem is, I have some measurements. From these measurements, I don't know the value of Q. Huh? What decrease?
When the temperature decrease, it's cooling, right?
Why? But there is a heat generation continuously, right?
Okay.
There is a heat generation in the problem. Okay. So please watch out. So I told you, that's why I told you there is a spin. So now I have a lot of measurements. Okay. So there are a lot of things which are going on. There is a big, there is a factory, and when some are generating heat, and there are some things which are generating heat, some things are cooling, and this thing you're observing. There is a centralized observation room. You're watching various systems, and sometimes you make an approximation that in some particular subsystem, it is spatially isothermal, lump capacitance can be obtained, and then you're watching the temperature. Based on watching the temperature, if you do all this forward model, inverse model business, you'll be able to find out what will be the Q and what will be the H in this problem, or rather, what will be the steady state temperature and what will be the H in this problem. From that H, if there is malfunctioning or if it is faulty, then you may put one fan, or you may redirect the room air conditioner towards that. If there are some hot spots, you will try to minimize the hot spots. So these are some of the interventions, engineering interventions, which we will do. But so that's why I'm starting from simple and proceeding to the complex. So you should be able to get a handle on this. Now, the solution to, and then, okay. So initial condition. T equal to 0, T equal to Ti, or theta equal to theta I. Okay, it starts with a particular initial temperature. Let's say it starts at 100 degrees centigrade, and then it can start with T infinity also. Let's say it starts with Ti, doesn't matter. Okay, then we want to find out. So what happens? All right. So now, to make it simple, let Ti be equal to T infinity. Okay, therefore, theta equal to 0 or T equal to 0. Okay, so this is the condition. Now, MCP equal to Q minus HA into theta. The solution consists of two parts: the complementary function plus the particular integral. The complementary function is obtained by setting the Q, this term, equal to 0. Okay, this you must have studied somewhere in maths. I hope all of you know that. Even if you don't know that, no problem, you can figure out from what I'm saying now. So the complementary function is basically MCP d theta by d tau minus HA into theta. Okay, so theta equal to yes, just copy this. I think I'm going a little fast. Just copy this and try to absorb what I'm try to assimilate what I've done so far. What will be this equation number? 6, huh? Okay. Is this fine? Can we proceed? Anybody has any doubts? Is it fine? Just do a thumbs up. Or if there's any problem, ask me. Okay. Thank you, Vikas. Okay, fine. All right. Now the particular integral is visible, is evident upon inspection. Okay, the particular integral by inspection q theta equal to q by ha. How do I do that? So if I do this, let's say MCP now, please do this. So if I substitute this d theta by d is equal to 0, so this theta is q by ha. Ha will get cancelled. Q minus q equal to 0. So my proposal, it is a proposal that the particular integral is q by ha is fine because it satisfies the original differential equation. Is this clear? Please let me know if there's any problem. Some maths prof must have taught you somewhere. Is this clear to you? Without this also, it is possible to solve by proposing theta in a different form. Okay. Siddharth says it's okay. All right. Anybody else? Of course. So for some problems, it is not possible to get the particular integral in this. Otherwise, your Mathematica will do it, or you do it here numerically, or whatever. So there are many methods available. If it is not analytically possible, it doesn't mean that we have to weep, we have to cry, oh, Newton, you failed me. I mean, there are 100 ways to solve problems. If analytical solution is not available, so be it. We'll solve it using some other method. Therefore, theta equal to a into e to the power of minus tau plus h. At t equal to 0, theta equal to 0 now. Okay. Please note, we did this. At time t equal to 0, we assume that initial temperature Ti to be T infinity. Therefore, I lost track. So this is 7. So the general solution is given by this. The general solution is given by this one. We substitute this. Therefore, 0 equal to a into e to the power of 0. Yeah, please complete it and tell me the form. I'll give you 2 minutes. I seem to be doing all the work myself. Just take 2 minutes and complete the form, and please connect it to what I have done yesterday. So what I wrote yesterday, the form from which we developed the Gauss-Newton algorithm, it is not some fancy stuff which doesn't come in heat transfer. So I have proved to you, I will have proved to you that this is a form which occurs very much in everyday heat transfer practice. What is that form? Y equal to A into 1 minus e to the power of minus bt. That minus b may be 1 by tau, A could be some theta I or what have you stuff. But that form is more important. And yesterday we figured out that the form cannot be linearized. Therefore, we need a Gauss-Newton algorithm. Yesterday we did some hard math on how to get the Z transpose T, Z operating on delta A, Z transpose T operating on D. So now 2-3 minutes, you just arrive at the aha moment yourself. Get a form which is similar to what we got yesterday. Therefore, get yourself convinced that the Gauss-Newton algorithm is indeed required, because there could be forms which are like this. There could be forms which need not be like this, which are non-linear. Still, the Gauss-Newton algorithm can be used because it just expands a function in the vicinity of your initial guesses. So let there be any function. Let there be a function which cannot be differentiated at all. Even then, the dou f by dou A, dou f by dou B, dou f by dou C, we can get it numerically. Therefore, we have a way of handling non-linearity in the world. So pranams to Gauss and Newton for teaching us how to approach a non-linear world. Okay, so please do it.
In assignment 2, question number 2, in weighted LSR. So,
Siddharth, just first let's stay with this.
Okay, sir.
This is okay.
Yes, sir.
Okay,
so can you discuss it in the end
you
of
just
the
tell
class?
me it's okay.
Maybe then.
Yeah. Please ask me in the end of the
Okay,
class. Okay. All right. Okay. You just write it on chat so that I don't forget. You just write it on chat now, Siddharth.
Okay, sir.
You write it on the chat now. Theta equal to. What a beauty. Y equal to A into 1 by d to the yesterday's class. So what is the difference between an engineering class and a mathematics class? Mathematics, I'm not saying belittling mathematics profs. What I'm saying is you should be able to connect. That's why we are engineers. We don't do science just for the sake of science itself. I can just come to the class and say that let y be expanded at a and b as a function of this thing like this. Let y be equal to a into 1 minus e to the power of minus bt, blah blah blah. But what is t? What is a? What is b? What is y? As an engineer, you have to say that. So I'm saying that, and then you should not leave the teacher. How does that form come? So we have taken the trouble to give you an example where such a form comes. Therefore, it is not just a mathematical abstraction. Many engineering problems these come. If these do not come directly, if the problem gets little messy, instead of getting t as a function of time alone, you will get x, y, z, t. In that case, the forward model, you solve it using COMSOL or Fluent, or write your code in MATLAB, Python, R, and then the inverse problem will be tougher. But if you know what is the general principle for solving a simple problem by doing paper and pencil work in the presence of a prof in the class, that means you can extend it to any difficult problem. That is the whole idea of education. Is that okay? So, but in one case, you should know where it comes from. That where I always, if you see my teaching, I always try to connect to where is it useful? Why is it useful? Why is something required at all? Why should we study inverse method? Why should we study heat transfer at all? These questions you should ask. Any course, you should ask this question. All right. Know how you can get anywhere. There are enough number of online classes, online resources, e-books are available. You can get even from MIT, Stanford, Prof, fluid mechanics, heat transfer. But please see whether no why. No why is answered. How many profs answer the no why? Concentrate on the no why aspect of things. Know how anyway. There's a lot of know how available. You can pick up. Okay, there's so many. You can register for a course. This you can do. You can have so many certificates. But you should know why it is coming in. What is the siddhant? What is it that we are doing? What is it that we are trying to understand? In this fast world, trying to accumulate knowledge, accumulate, learning more techniques, you should not forget, you should not lose track of why all this. I'm always, whenever I always ask this question, even PhD students, I'll ask, why this at all? It may be great, it may be fancy, whatever. We are engineers. Why this at all? Can't it not be done by some other technique? Can't it not be done by something which we already know? These are very essential questions which you have to ask. Okay. Now, other examples. Okay. Let's say there is a chip. Okay, the chip is generating heat at the rate of Q. You want to cool the chip, so you put a heat sink. Huh? So you put the heat sink like this. So this is the heat sink, and this is the fan. Thank you, Chinna. So this is the fan. So this is you want to cool this. Okay, so you want to cool this. So you can consider the whole thing to be at one temperature. So this is basically mCp dt by d tau equal to Q minus. This could be, but this H could be the H total. Huh? This H could be, I can put on these pins on the heat sink, I can put a black paint. Okay, this could be H convection plus H radius. This is for starters. Okay, if this fin were to be taken to outer space, so this could simply be mCp dt by d tau Q minus Q radiation. The Q radiation, I cannot simply write it as epsilon sigma all that, because one fin is interacting with another fin. So I have to use the radiation method, which I taught you in the heat transfer course. So this becomes a messy problem. But it is not a theoretical problem. This heat sink is used in satellite cooling. Okay. So you can see that. And the motivation for the inverse problem is you might have assumed some emissivity. But if you start getting measurements, so you will, as an analyst, you want to find out whether the emissivity is okay or not. What is, and it is changing. What you expected is different from that. Then what is this? So how does it enter? How does it get fed back into the system? Your next launch vehicle, in your next mission, you will correct the emissivity. This is how we, so nothing is perfect. Nothing. The whole world is going towards improvement. As an individual, as a society, as a nation, as an institute, whatever it is, everybody thinks that we'll improve. What is the eventual improve? If everything improves to a perfect limit, if nothing else can, if we cannot improve it any further, we don't know that will be a theoretical limit of maximum entropy. And because activity can proceed only when entropy increases, if entropy reaches the maximum, no further increase in entropy is possible. There will be a collapse. That is a thermodynamics. So that is at infinite time or whatever. Let's not worry about that. Now let's come to brass tacks. So in this case, if this heat sink is taken outside, we are in trouble. Okay, it becomes a lot more difficult. Okay. Now, second, apple kept in a fridge. The apple kept in a fridge. Apple also is a, so there is a QV, which is due to the metabolism. So you go to the shopping center, buy the apple, it is about 30 degrees centigrade, you put it in the fridge. Okay. In the fridge. Okay. So now it is cooling at infinity. Okay. Shalu, what is it? You are saying the video clarity is poor. Our
Yes,
internet
sir,
is stable.
it's
I don't
blurry.
think
I don't know if it's from my end or your end.
Yeah, I think Suraj has to tell me. Suraj, is it okay?
Now it's better, sir.
Yes, sir. No, okay, sir.
Yeah, I think you are on some, see, we are on high internet. So internet should, even if this goes, I have a Airtel, which is basically much lower than this, but still the resolution is better. Okay, what happened to, I'm not able to see myself. Where did I go? I'm here. Okay. All right. Okay. So apple kept in a fridge. Okay. And for example, you take a bucket of water. You take a bucket of water. Water in a bucket. You put your immersion heater here. Okay. Assume that that immersion heater, just for starters, just for the immersion heater, the water, the bucket, everything is at one temperature T. And this is supplying a heat of Q. Then again, this will be mCp dt by dt equal to Q minus HA into T minus T infinity. So even if you leave it on for a long time, so long as the water is not sufficiently evaporated, you will see that it has reached a steady state temperature of 80 or 85 degrees centigrade. After that, slowly from the surface, you will start losing water. Okay. So it will reach some 80 or 85. That you can work out. What final steady state temperature will reach depends on this Q minus HA delta T. All right. That is why you should say that the H for air is much lower than the H for water. Okay. Therefore, you should never leave your immersion heater without the water in that. All right. Okay. Now we have established the case for this. Now, Suraj, just show the problem now. What will be the problem number? Can somebody tell me the problem number? So, Suraj, please show the problem.
Please enable, sir. Actually, host disable participant screen sharing. Host disabled participant screen sharing, sir. Please accept, sir.
Yeah, I have done it.
Sir, like what is it?
Who is it?
Yeah, this is Pradeep, by the way. Sir, in the board you wrote something like metabolism. Is it metabolism or like near that immersion heater? You wrote some M word, right, sir?
No, metabolism of the apple.
Okay.
Apple. See, just cooling of an apple also there is a QV.
Yes, sir.
So I gave you three examples. One is this some body. Then I told you, I gave you three examples. First was the heat sink, second was the apple, third was the immersion heater. So in all these three cases from diverse applications, there is some heating and cooling which is involved. It is all these lead to all roads lead to Rome. A into 1 minus e to the power of minus b. Hey, Shalu, is it okay now? This clarity is okay? You pin his video.
Yes, sir. Yeah.
Yeah. Okay. Problem number 10. I will read out the problem. You have to copy this. Consider the heating of a first order system discussed in the class. Suraj, what you can do is, Suraj, are you listening?
Sir.
Only this problem sheet without the solution, convert to PDF and send it by email and WhatsApp to everybody after the class. Very good. Okay. Now, so class, please note that. Please take down this value. So I will do some hand holding at least for one iteration. I will do it live in tomorrow's class because this is very important in this course because the nonlinear regression is the basis for several inverse problems. Okay. More important than even the linear regression because linear regression some other prof must have taught you. Nonlinear regression, I don't think you have learned. Has anybody learned nonlinear regression anywhere in any course in IIT so far? Can somebody respond? With examples and hand calculations, have you done this? There can be only two answers, right? No. Okay. That is why it is important that you learn it properly, right? So I'm telling you that even if you don't, if the problem doesn't have a no, so many things are going on in my mind. Okay. So I had to hold it back. What I meant to say was, even if it is very difficult to find the derivatives, the Jacobian matrix, you can do it numerically. But what my mind was racing, it went to the next step. What was the next step? Even if there is a no forward model, there is no problem. Even if there is a no forward model, if you know the inputs versus outputs using data science, machine learning, although this will be of interest, particularly to the data science dual degree. How many of you are there? Quite a few of you are there, right? In the data science program. Now, somebody should say yes, 2, 3, yes. Just say yes. I'm not able to see you because I'm seeing Suraj's screen. Are there some data science guys? ID, interdisciplinary dual degree program. Now, what I'm saying is, even if there is no forward model, you can use a neural network and drive it. All that we can do a little later. Now, after S. Balaji finishes his lectures. Consider the heating of a first order system discussed in the class. From the transient experiment, the following data are collected. That is the theta, t minus t infinity, and the time, okay, against the time. The solution is known to have the form theta equal to a into 1 minus e to the power of minus bt, the celebrated form, with initial guess of 35 degrees Celsius for A and 0.004 second inverse for B. Perform 2 iterations of the GNA. So for the GNA, initial guess is required. We have given this. Report the residuals. That means theta I minus theta fit I whole square sigma I equal to 1 to 6. Okay. Suraj, can you go up so that you just show only the data now? Go up and blow it up. Make it bigger, Suraj. Okay, please copy down the data. So tomorrow's class is, please bring your calculators. I'm going to work out one iteration. Second iteration, I'll ask Suraj to show it on the Excel sheet. Okay. All right. So please copy down 3 columns and 7 rows. First is the header, 6 times and 6 temperatures. It's well worth it. Do it yourself. Then you'll never forget the Gauss-Newton algorithm in your life. 10 seconds, 41 seconds, 79 seconds, 139 seconds, 202 and 298 for those people whose screen is not clear. 10 seconds, 3.1 degrees Celsius. 41 seconds, 11.8. 79 seconds, 21.1. 139 seconds, 29.8. 202 seconds, 37.4. 298 seconds, 42.5. What am I saying? Time and the corresponding theta. But what is theta? T minus T infinity. Suraj, did we give it? Is T infinity required in the problem? Not required, right? Huh?
No required, sir.
Not required. But finally, if you want to find out the hot spot,
Yes, sir.
or you want to find the temperature,
Yes,
T
sir.
infinity.
This was required.
Please. Yes. Yes. Okay. Siddharth, what is your question? Siddharth.
Sir,
Go ahead. Shoot.
in
Siddharth.
assignment 2, question number 2, the weighted LSR, the only thing we have to do is like in the formulation of the residuals error, like we have to like put sigma I square. And
Correct.
that sigma I is
Correct. 1 by sigma I square.
Yes, sir. And that sigma is the error associated with
1 by sigma I square is whatever is given, plus or minus, that is given, no?
that term. So like in the matrix form, we get like 1 by sigma I square in every term, kind of. So that is the only difference.
But the derivation, we have asked it as part A. Once you complete the derivation, substitute that.
Okay, so like we just take again derivative with respect to A and B and solve for.
Correct.
Okay, sir.
That's all. Because don't take derivative with respect to WI and all that. They are all known. Okay.
Okay, sir.
All right. Okay. Chalo. So we will now end the lecture. I'll end the meeting for all. So we'll meet you at 9 o'clock tomorrow. We are going to solve this Gauss-Newton problem. So don't miss tomorrow's class. Tell your friends. So definitely some problem will come in quiz 2 or end some. Regardless, if you don't know nonlinear regression, several things like Liebenberg, Marquardt, Tikhonov regularization, Jacobian, an important part of the course you will miss. So please tell your friends who have been sleeping or saying that, okay, I'm a genius, I can watch videos, and ask them to come to tomorrow's class. All right.